And it's a real honor to be here today. I'm delighted to be asked to give this lecture, and this year in memory of Peter Armitage for the first time. What I'm going to talk about will be, first of all, the way in which Peter introduced the idea of sequential analysis to medical trials, building on framework from an industrial setting and then the developing field of clinical trials, which was pretty new at the time. And then I'll move on and talk about later developments. And I'm very grateful to the previous speakers because I'm going to be able to refer to various topics along the way and say, well, you know, Sue told us that, John told us that already, and add my little contribution. Let me say a little bit about myself. Simon reminded me that, well, we're actually contemporaries. We both arrived in Cambridge as undergraduates in 1974, so 50 years. Time has passed. And we got to know each other because we did the diploma in statistics, and that was a group of, I think, 12 students. John followed 3 years later, I guess, doing the same program. After that, I went to Cornell, did my PhD with Bruce Turnbull. The topic I'll say a bit about in due course really came from reading Peter Armitage's book on sequential medical trials. And I thought, there's testing, but there's also estimation. Can we bring those together? And that's what I worked on. I nearly worked for Peter. When I finished at Cornell, I came over to England and had 3 interviews lined up in a couple of days, one of which was to do a postdoc with Peter. But the first interview was for a lectureship at Durham University, and they offered me that. And I thought, well, that's a permanent post, so that's what I took. But I did go down to Oxford and meet Peter the next day and had a conversation. And I feel I've seen very little of him, actually, given how closely we worked since then. But I'll talk about other times that we have met. But let me get to Peter's work. And as I say, he introduced sequential analysis to clinical trials. Well, where did these methods come from? If you look in the sort of engineering area, you'll see that early in the 20th century, there were sequential sampling plans. So if you had a factory and you received a batch of components, you might want to test them to make sure they have suitable quality. And that could be time consuming also. If it's destructive testing, you're losing some of the batch. So people did invent, say, 2-stage sampling plans. Here's an example of such a plan. So what's going to happen is there's a total of 95 components to be sampled. And if 4 or more of them are defective, that batch will be rejected. And 0, 1, 2, 3, it will be accepted. But what's going to happen is that the first part of the sampling is with a sample of 36. And obviously, if you've got 4 defective already, you can stop because it's clear that this isn't going to work out. And in this case, if you had 0 defective out of the first 36, then you're allowed to stop and accept the plan. So this will cut down the sampling a lot if there really are seriously more than the acceptable number of defectives. And even if it's a very good sample, you can stop early and accept it. So this sort of idea has been around for a long time, but during the Second World War, there were a lot of steps forward because there was a great interest in testing munitions, testing strategies for doing things in war, that led in the United States to Abraham Wald developing a very famous method known as the sequential probability ratio test. And in the UK, George Barnard worked on similar sorts of methods. He was in a unit called SR17 in the Ministry of Supply. And Barnard published some of his methods later. And in fact, well, what did Peter Armitage do? He was born in 1924. He came to Cambridge as a student in 1941 and started the mathematics tripos. But then he interrupted his studies. In 1943, he went to work in this SR17 unit. So he worked with Barnard Other people who were working there were Dennis Lindley and Robin Plackett. Good company. Peter returned to Cambridge in 1945, finished his degree in mathematics. Let's just turn to clinical trials. We've heard already, I think Vern Farwell told us about the early clinical trials and the move from an alternation procedure to randomization, and this streptomycin trial of Austin Bradford Hill was conducted in 1946. What I read was that I think Bradford Hill was a bit nervous about randomization. He thought that people might think it was strange, but actually the doctors quite liked it, and it very soon became the standard. That was the way to conduct clinical trials. Peter Armitage, after the war and after I think a little work elsewhere, he moved to the Medical Research Council's unit in the London School of Hygiene and Tropical Medicine. And then as part of that work, although he was obviously doing other important things with Richard Doll, who we've heard about, one of his activities was to look at sequential methods in clinical trials, and he went to the States and visited Schneiderman there, and they worked on some new proposals. Let me just say a little bit about Wald's SPRT, sequential probability ratio test, because this really was a landmark, and people still like it today. It had a really neat piece of mathematics to construct the test. And this is a version where there are two arms, because we're testing a null hypothesis of something equal to 0. I've said observations, but maybe these are differences in a pair of patients, one on treatment A, one on treatment B. So the null hypothesis that this mean mu is 0 would say the two treatments have the same effect. And it's being tested against a two-sided alternative. And really what's going on in each of these arms is if you're in this upper arm, you're carrying on because you can't decide between mu equals 0 and mu greater than 0. And in the lower arm, you're distinguishing between mu equals 0 and mu less than 0. And you'll notice that the continuation region keeps going forever. These are parallel lines, so they just keep going. There's no upper limit on the sample size. It will terminate with probability 1, but it's quite possible that you'd get 2 or 3 times the fixed sample size that you'd have needed to have a test with the same error rates. And in the medical setting, that really doesn't seem right. If your trial could be done in 3 or 4 years in a fixed sample way, you wouldn't want to risk that it might take 7 or 8 years, right? You might add an extra 6 months or so and be comfortable with that. So Peter worked on restricted sequential procedures, which had a maximum sample size that was a little bigger than the fixed sample size, but nothing like as much as the SPRT. And I'd read these papers and I was looking back thinking, but actually in 1957, what was going on? How did you calculate properties? How did you get a formula and evaluate it numerically? So what was actually happening in this procedure was there was some very nice maths. And there was just a minimal amount of calculation. So let's just look at the procedure. So now we do have observations xi, which let's suppose are the difference in response from a pair of subjects, one on each treatment arm. The mean is mu. We want to test the null hypothesis mu equals 0 against a two-sided alternative. The two-sided type 1 error probability is 2 alpha, so you've got a probability alpha in each direction for rejecting the null when it's true. And power 1 minus beta at plus or minus some specified difference. And Armitage's procedure looked like this. So we have a stopping boundary. There's an upper straight line edge, a lower straight line edge. If we cross those, we can reject the null hypothesis. And obviously, if we go out here, we'll say mu is positive. Let's say that means treatment A is better. Through the other boundary, we stop and say mu is negative, so treatment B is better. And if we're still going all the way to the end, at this final sample size, capital N, we end up accepting or not rejecting the null hypothesis. So these are straight line boundaries. say the summation of the xi is equal to a plus bn or minus a minus bn. So how are these set up in a way that has type 1 error to alpha and power 1 minus beta where it's wanted? So Armitage brought together two ideas. One was from the sequential probability ratio test. Basically, what he did was to say, I can use the same trick that Wald did to make the ratio of the probability of, say, exiting the upper boundary when mu is 0 versus mu equals plus mu1 equal to a certain amount. And I make that the ratio of my alpha and beta. And that's what these choices are doing. But then I still need to make, say, the power equal to beta. And so there's a formula here that one needs to satisfy. And this comes from work of Maurice Bartlett on diffusion processes. I think I read a commentary on this later by Schneiderman saying, oh, there's this young guy, and he came and he got these great ideas and put them together. And this still needed calculating, right? What have you got? A slide rule, a book of tables. Where did tables come from? Well, when I was doing the diploma, there were some of these things at the back of the stats laboratory. These are Braunschweiger machines. And the way you do a calculation is you move some little levers up and down this part of the machine, and you turn the handle a certain number of times, and you shift it along and turn it again. You can do multiplication, right? And if you are a research student, so for the research students here, this is how life has changed, right? If you're a research student, you have to maybe spend every Wednesday afternoon doing your stint on these machines, eventually producing books of tables, which would have contained the cumulative standard normal distribution that Schneiderman and Armitage were using in their calculations. So the fact that Peter Armitage was able to make a test that wasn't the SPRT, that did have a finite and sensible upper bound on the sample size, needed some pretty neat maths. And also a bit of work in the background to do the calculations. But that wasn't the end. So one thing you'd notice in the previous diagram where there was a straight line boundary at the end, obviously if you're getting close to that point and you're still near sigma xi equals 0, it's pretty obvious what's going to happen. You're not going to cross one of the outer boundaries. So Schneiderman and Armitage in their next paper said, well, let's bring this wedge shape in a boundary in a way that has very little effect on the type 1 error or the power, but allows us to stop early, particularly when the mean is close to 0, when the two treatments are actually very similar. The formula to do with the points on the wedge, it was a bit like that formula we've just seen. The only thing was it had to be calculated repeatedly at lots of points to do the whole inner boundary. And in their paper in 1962, they gave results for various cases with different alphas and betas and different numbers of observations. So this was going to require more computation. So what did you have in 1962? Well, computers did exist. In the paper, they say they used the NIH's IBM 650 computer. So I looked up what was the IBM 650. That's what its magnetic memory drum looked like inside, and that's what an operator looked like. And in the blurb, it said that it was very fast because it could do a calculation in the same time it takes a fruit fly to flap its wings. So this meant about 400 operations per second. And this was enough to do the calculations that they needed in 1962. So I'm not sure how much my laptop or my PC does. It does more than 400 things a second. And I Googled, I found the language is these days, at least this is for a supercomputer actually, is a petaflop. A petaflop is 1,000 billion operations per second, floating point operations. Your laptop won't do as much as that. You have to lose a few zeros, but you're still a billion or more times as fast as the IBM 650. In fact, your washing machine or your fridge probably can do more than this. So I think Peter was he was a computing expert. He was bringing something other than statistics and medical insights into this field. I think very much ahead of his time. So that took him to one point, the restricted procedure with its wedge. There was some debate about, were these sort of things necessary? Say clinical trials had arrived, they were being conducted. People were looking at the data as they accumulated during the trial. And the question arose, is it okay to look at my data and stop when I think it's telling me something interesting? What if I just do a significance test at 5%, stop when it looks positive? And that question had to be answered. Did it really cause an inflation of type 1 error? And the paper by Armitage, McPherson, and Rowe actually did calculations to give a proper answer to the question. It's obvious that it does inflate type 1 error, but by how much if you do the same test over and over again? Because these tests are not independent. You've got one set of data that's just growing in size. So this is the scenario. Again, we've got our normal mu1 observations taken in sequence. We look at the sums. And let's say after each new xi, we do a significance level alpha, or this is, yes, level 2 alpha, two-sided test. What happens to the type 1 error probability as the number of analyses grows? Notice there's one analysis after each new observation. We're still in the world of fully sequential procedures. So to do this calculation, we need some numerical analysis or some bit more theory. And what Armitage, McPherson, and Rowe did in their paper was explain how the density of this sum at each stage would change. If you didn't have any early stopping, it would be simple. It would just be a cumulative sum of normals, so it would be normal. But the paths that cross a boundary, we lose. So you have to do something a bit more clever. And there's a recursive formula that allows you to say, if I know the density at this point after the n-1 observations, and I allow for the fact that I'm going to stop if I'm over a top boundary or below the lower boundary, I can do an integral. This is just the transition from one observation to the next. I can find the next density. Having done that, you've got these nested integrals. You're trying to do a calculation. You have to go to numerical methods and replace integrals by sums. And so numerical integration was brought in at that point. But they were able to do that. They were able to get very accurate answers, this time using computers here in London. And that allowed Armitage, McPherson, and Rowe to present results and say, if you just test your data once at level 0.05, you get a type 1 error rate of 0.05. If you do it twice, that doesn't quite double, but it does go up a lot, 0.083, and so forth. If you keep going forever, you will eventually get significance at the 5% level. My reading of the paper was that the contribution of Rowe was some kind of earlier work where they'd made the same investigation, but using simulation. And part of the comments in the paper was how the numerical integration methods turned out to be more accurate than the simulations. And so that was the way to go forward. So this is really a cautionary result saying, don't analyze your data over and over again and believe that you're seeing the same sort of information as if you just analyze it once and ignore the stopping rule. But also you could say, well, let's reverse engineer things. If I do want to look at my data after each new observation, and I want to test with overall type 1 error 0.05, then I should apply a lower nominal significance level in such a way that things turn out to give me 0.05 for the overall error. So if you have 5 analyses, you should conduct each significance test at 0.0158, or on the Z scale, 1.96 is replaced by 2.413. And the more analyses you have, then the smaller this nominal significance level becomes. And so they called this the repeated significance test. And this is a way one can do business. In the 1975 edition of Armitage's book, Sequential Medical Trials, there was quite an emphasis on this repeated significance test. So I think this was taking over in Peter's mind from the restricted procedure as a way forward. And these methods were used. So Peter wrote an article in 1969, and he referred to sequential trials, I think using the repeated significance test or the restricted procedure maybe, being reported in 50 papers in all kinds of areas of medicine. There's a summary of one example here. So this is quite a small trial. It was planned with a maximum number of pairs of patients equal to 66, a minimum of 9, and the boundary was reached after 18. No, sorry, after 18 preferences. Yes, 18 preferences. So pairs of patients, 1 on each treatment. And 15 favored the new treatment, 3 favored placebo. So that was pretty clear evidence the new treatment was working now. So this was pretty good progress. And given what Sue said about how slow the uptake has been, why didn't things just keep moving? Let me go off in a slightly different direction. The area has not been without controversy. As soon as you look at methods like this, particularly, the strange things that happen in frequentist inference are magnified in sequential methods. So it's good hunting ground for Bayesians to argue that you should do things differently. And Frank Anscombe, well, he was asked to write a book review of Armitage's book. And he, according to his article, he said, well, I started doing that, but it just grew into an article. So he published quite a long article in JASA. And the tone is interesting. I think it's very nice. He says up front, this is statistical polemic, thinly disguised as a book review. And in the summary, he was very frank. Sequential analysis is a hoax, he says. At the same time, early on in his article, he says, before I start criticizing this, Peter Armitage's work is going to have a really good effect. Its net effect on medical research will certainly be good. A little later, Peter wrote his answer, and I think his humor comes through here. He said, so this was a statistical polemic, thinly disguised as a book review. He said, this is statistical polemic, thinly disguised as a reply. And he doesn't want to strike an aggressive attitude. In fact, Anscombe had been at the SR17 unit with Armitage, Barnard, etc. So they were good friends, and they remained friends. They met quite a bit, I think, subsequently. I think there's a lesson for us here. You can have really intense debates, you can have passionate opinions, and you can still be nice to each other. And also, I think, as we saw in the quotes earlier on today, Armitage kept an open mind. Let me give a bit more detail, and this really goes into some of the things that I think Sue was describing. Or was it Sophia? I'm getting blurred at the end of the day. Well, there's response adaptive randomization here, so it must have been Sophia. So on the one hand, Anscombe was saying one should be Bayesian. We shouldn't be tied to type 1 and type 2 error rates. But he liked this horizon problem. And he was saying, what you're really doing in a study is you're choosing the treatment that's going to be given to future patients. And if there are so many patients in our study, there'll be another group of patients who receive the treatment that we chose in the future. So that was his idea of horizon, which also goes back to the paper of Colton that Sophia described. It's a little difficult. How do you set this horizon? You're sort of waiting to see how far in the future will it be before some other treatment comes along and replaces all of the things that we do now. I think other authors later have said, well, you don't have to be too precise about this. An order of magnitude will be a good starting point. So the idea is that you say, we've got a capital N population of patients. We'll have 2 little n in our trial. We'll make a decision after that point as to which treatment we recommend. And then everybody else, n minus 2n, will get this recommended treatment. And so you have to worry about making the wrong choice, in which case you've got a lot of patients getting an inferior treatment, but also spending too long in your trial getting exactly the right treatment when you really could have stopped because you knew with enough certainty stop. So this could be sequential, and the little n here could be a random variable. And Anscombe drew some pictures and said, here's what my stopping boundaries look like, and then here's what Armitage's look like, and they're very different, so clearly we're doing something different. And of course, Anscombe's inference was that his was the right way to do it. What did Armitage say? Well, he thought that what Anscombe proposed wasn't necessarily too practical. I think the horizon was an issue. And also maybe the idea that at the end of your trial, suddenly medical practice would change and everyone would move to the treatment that you said was better, was a little naive. He raised the question of ethics. How do you trade between the benefit of patients in your study and then the benefit of future patients? One thing I would note is that when you look at this now and think of what happens with a new drug that a pharmaceutical company is producing, the regulator will say, you've got to prove that this is better than the current standard treatment, assuming that there's no great difference in safety or other features of the treatment. So really, it's not a two-sided test at all. It's a one-sided test. Can you show this is better, or is it the same or worse than the current treatment? And it's a testing problem. The regulator will say, we need p less than 0.025 one-sided, right? 0.026, your drug doesn't work. 0.024, it's wonderful. So that goes against this treatment selection approach that Armitage is working on. Nevertheless, that formulation was attractive, certainly to mathematicians who found they could make bandit problems and do interesting things. I was looking for Bather's red paper because I remembered Peto's comments, but I found a different one. He had a red paper in '81, and it was John Anderson who was the naysayer on that occasion, saying that this wouldn't work. And it was, I think he was going even further and saying, well, we don't even want sequential trials. We just want to get to the end and have lots of data so we know. It wasn't just the adaptive randomization. So you could say this was a dead end, although aspects, response adaptive randomization, have carried on. And in fact, maybe there's a bit of a comeback, because in trials with rare diseases, numbers of patients are small. It may not be possible to run a trial to show with high significance that new treatment is better than old. And also, it may be that for this disease, all the patients in your country or even some wider area are in your trial. There is no external set of patients to worry about. So the focus changes and the decision theory ideas maybe make more sense. So again, when Peter always hedged and said, well, maybe there's something else to think about, I think there's some truth. And regulators they haven't fallen over backwards, but I think they've shown some willingness in trials for rare diseases to look at the world a bit differently. Now, I think I've pretty much covered what I wanted to say about Peter's early work. What happened next? So there are various things that come into play. In fact, there are so many. I'm just going to focus on some of them. One thing was this issue of a fully sequential test, where after every new observation, you look at your data and you see, is it time to stop? And There's a report of a meeting by some experienced statisticians talking about these sort of issues where Lawrence Shaw, who worked for the Veterans Administration in the USA, said, well, the way we do things is we run a trial, and then every now and then we make a report to the sponsors, and said, you know, you could make that into an interim analysis. He called it a block sequential method. That was in 1965. It was actually quite a bit later that the papers of Pocock and O'Brien and Fleming, which I think as a landmark ones, prompted the widespread use of group sequential tests. I think in the meantime, and we did have a reference to this, Clint McPherson had also pointed in this direction. So a group sequential method, you really come at it from the other direction. You say it's like a fixed sample study, but every now and then we will take a look at the data, maybe 3 times, maybe 4 times, maybe even only once, just one interim analysis. Quite a popular choice. And this fits in well with the way large multi-center, multinational trials run. You can't just say tomorrow, I'm going to look at the data. You have to get whoever's looking after your data to clean it and to prepare it. The data monitoring committee who are going to look at the results, they've got to be booked into in their diaries 6 months in advance to have a meeting date, because all but one of them are doctors, right? The other one is the statistician, who probably has a busy diary. So group sequential really fits in lots of ways. And do you lose anything by not looking so frequently? Well, we'll see. So Pocock, who was a research student of Armitage, as we heard earlier, he said, well, and this is really building on what McPherson was saying, we can just do this repeated significance test, but instead of the XIs being a pair of patients and the difference between them, this could be a result from a group of patients. You get the same normal random variable. So if we have 5 groups of patients, we get exactly the same kind of joint distribution of our Z statistics under the null hypothesis. We do the same calculations. So he was using these numerical methods of Armitage, McPherson, and Rowe, the recursive formula to get densities and the numerical integration to evaluate the numbers. Pocock, I think, did a lot in this paper that was really, really important. He said, having done that, we can control type 1 error, but also we can still do all the things that you want to do. So he could tell us what group size should you take to meet your power requirement. And he went beyond normal observations with known variance. He said, actually, if you think of this as a significance test, so whatever distribution you're working with, it could be a t distribution, it could be some non-parametric test, convert your p-value to a z value, convert your statistic to a p-value, and then look and see how does that compare to whatever the p-value on the standard normal is at 2.413. So you apply this alpha prime, right, the nominal significance level at some small value that gives you an overall 0.05. And so Pocock showed by example that this worked, and the fact that there's some approximation in here in behaving as if your data are sums of independent normals didn't really seem to affect probabilities. And that gave a boundary that was constant on the Z scale. So it's a repeated significance test at the same level all the way through. Slightly later, O'Brien and Fleming proposed a different test. It was group sequential, so a lot of the features are the same, but the boundary is a different shape. If we'd worked on sample sums rather than standardized statistics, this would have been a straight line boundary. And what that means is it's pretty wide early on, but it gets narrower, and that the final analysis, you end up testing at something not very different from the 1.96 or the fixed sample test. And in some ways that's nice because, well, it's one of these strange things, you know. What if you've got 1.98? No. What if you've got, yeah, you've got 1.98 at the end. So if you've been doing a fixed sample study, you could declare your treatment worked. Because you've looked at the data along the way, it doesn't mean the same thing. Well, you have to behave that way if you want to protect type 1 error. but it does seem odd. And so keeping this final cutoff close to 1.96 it avoids some embarrassment. Also, I think people they're happy to have quite a high hurdle early on. The data are a bit immature. You're not necessarily giving up much power because you really have to work hard to get over these. Interestingly, O'Brien and Fleming, they didn't do numerical integration. They did just blunt simulation. So they found the boundary points by doing simulation and saying, from 10,000 replicates, what's the 5% or 2.5%, most extreme value? That becomes the boundary value. And when they reported properties, power, expected sample size, they had 1,000 simulations. And in fact, if you look in their tables, there are some rather anomalous things. You think this number has to be bigger than this one, but it seems to be smaller. That was simulation error. So they hadn't taken advantage of what Peter had already introduced as some very neat ways to do these calculations accurately and pretty quickly. I said, I think really one ends up not choosing between two treatments. You've got a new treatment and a control, and typically you're trying to show the new treatment is better. So you should be doing a one-sided hypothesis test. In that lower arm of the SPRT that I showed you, you're really, if you're down there, you're saying, is my new treatment the same as the current standard, or is it really worse? Let's randomize some patients just to see how bad it is. Well, obviously that's not a good idea. So one can stop early for futility and just say, my mu's have turned into thetas now. Theta is less than or equal to 0 down here, and I don't really need to distinguish between equal or less than, because either way, I'm not going to pursue this new treatment. So the Metzen were picked up on that, and they proposed some boundaries. Slightly funny looking. Why doesn't it come to a point? But this is what they did. Also, reading this particular pair of papers, I thought, gosh, I can see one reason why these methods took on slowly. It was really hard to figure out what was going on. Notation, presentation. I think there was a typo somewhere in one of the key formulae. But I managed to get a picture that looked like theirs by putting something in. But this obviously was a key step. One-sided tests, not two-sided tests. The other thing to think about is, what about these non-normal cases, or even normal data when you have some covariates in a regression model? How do the test statistics, so this is my treatment effect theta now, at analysis K, how does that behave over time as I get more data and I move from analysis to analysis? And it turns out they behave very nicely. If your data are normal to start with, not surprisingly, your sequence of theta hats is multivariate normal, but it's got a certain covariance structure. So the covariance of two estimates is the variance of the later one. And this holds in great generality. Any normal linear model, you can have longitudinal data, covariates, whatever, you get the same result. With parametric models, you get the same result asymptotically with the same assumptions that you need to get it in one fixed sample analysis. Survival data, you get these. That took additional approaches. And Bruce and I had a paper. There was a paper next door to it in this edition of JASA, where we proved these results. This was rather interesting that these two papers came out side by side. We had a chance to comment on each other's paper. And we both said the other paper is a special case of our paper. And I think we were both right. But we did it very differently. If you want to see why this works, I think I'd start with my paper. But if you know what semi-parametric efficiency is all about, then read the other one. But this is important. It means we can underpin methods, and we don't need to make whole new different procedures every time we move from normal to exponential to Poisson or to any other distribution. Survival data, let me just say a little bit about, because a great many clinical trials are time to event or survival endpoints. And there's a lot going on here now, because patients will enter the study over time, and then at an interim analysis, we'll have right censoring simply due to the fact that this is as far as we've got. And then the same patient at the next analysis will have more follow-up. They might still be censored. They may have failed by then. So it's a complicated setup. It's a little hard to imagine that this means that if you do a sequential log rank test, you're going to get some nice output. But it turns out you do. This falls into the general framework, or has the same general joint distribution for test statistics, whether it's log rank or parameters in a Cox model being estimated. But one thing that you realize is the information, in the sense of Fisher information, which is the reciprocal of the variance of the current estimate, that's going to be unpredictable because it depends on how many events have occurred. So if you have a survival endpoint and you say we're going to have our analyses, have the monitoring committee meeting, every December or every June, how much information you get at one of those meetings will depend on what's actually happened in the data. And the group sequential methods that we've seen described tend to focus on a setting where you have equal group sizes, so equal numbers of observations. In this case, it would mean roughly equal number of events between analyses. So how do you cope with the real world when that doesn't actually happen? So I've sort of switched from sample size to information because it's a bit more general. But when I talk about information, in a lot of settings, you can think of that as being equivalent to sample size. If you have responses with a parametric distribution, they're going to be very close. But in a survival study, information becomes some multiple of the number of events observed. So if that's going to be unpredictable, Land and Demet said, well, we can construct a sequential procedure by spending the type 1 error. We're back in the testing a null hypothesis against a two-sided alternative here. And Land and Demet said, well, specify your function. It increases with the amount of observed information from 0 to alpha. If you get up to the maximum target information, you just level off at state alpha. And the idea is we'll create the boundary in such a way that the cumulative type 1 error at some interim analysis will be this function of the observed information. So if you get more events in your survival study, you have a bit more type 1 error to spend at a given analysis, and vice versa. So this was an important step forward. It needed a bit of development to make one-sided tests, which really had a proper upper boundary and lower boundary. But one can do that. You can say we'll have a type 1 error alpha to spend when theta is 0. We'll have type 2 error beta to spend when theta is delta. That's some specified alternative that we're interested in. And we can do that with 2 error spending functions. So we do exactly the same sort of thing, but we set up the boundary so the cumulative type 1 error is f of I over I max, and the cumulative type 2 error calculated under theta equals delta is g of I over I max. And well, we're a bit light on equations. There's an equation. It's just saying what I just said in symbols. And the point is you can start at the beginning. You create the boundary step by step. You don't need to know what will happen next, right? As long as you know what's happened so far, you can get the current boundary point. So this is a very nice, flexible approach to deal with that unpredictable scenario. So what have we got? We've got Pocock and O'Brien and Fleming give us 2 different types of boundary. We've actually got a literature starting to appear on one-sided tests and now even more shapes of boundary. We've got error spending designs with error spending functions that need to be specified. So one can start asking questions. What's the best choice? What stopping boundary should we have? Or if we're doing error spending, what function f and g should we have for spending type 1, type 2 error? And when we say best, what do we mean? What are the constraints, and then what are the objectives? So this was a question that interested me. And the first thing I was interested in doing was formulating the question. We'll work in terms of information, because that's kind of mathematically simpler. So if we specify alpha, beta, and delta in this one-sided test formulation, we can work out the information that we would need to do a fixed sample analysis. Okay? And so that's a kind of benchmark if we're getting a lower expected information, we're doing well, but we don't want a maximum information that's much higher than this. And information will be a rough measure of sample size. It depends a bit on the setting as to whether that's a perfect thing, but it's a nice thing to work with when you're trying to optimize the procedure. What next? Well, how many analyses are we going to have? What maximum sample size do we allow? So we can talk about an inflation factor, which is the ratio of the maximum information that we're going to consider versus the fixed sample information. Of course, both of these are things to choose, and maybe we're going to think about them once we know what they deliver. So I would say let's fix K and R, find what's optimal, what that can achieve, and then we can look and see, do we want a different K because increasing it a bit will have a big improvement. And the same with this maximum information. How do the benefits of early stopping increase as we increase maximum information? So I've worked in that domain of saying condition on K and R and have equally sized steps in the information, just for simplicity. And then we can say what we're trying to optimize. So we've got our constraints on type 1 and 2 error. Let's try and minimize the expected information, but under what values of the treatment effect theta? We could choose a discrete set of values and say, let's just take a weighted average, maybe under theta equals 0, theta equals delta, maybe theta equals delta over 2 is important. We can put things into that formula, or we could do an integral. And if that density here was a normal density, that's going to turn out to be something that's quite manageable as well. So I looked into methods of finding the group sequential test that optimizes one of these criteria. The first approach I did was very crude. It got answers, and that's about all one can say about it in terms of finesse. Later on, I worked with some research student, John Eales, Stuart Barber, and we had a much nicer approach. One of the problems here is the constraints. You've got an optimization problem. You're choosing, you've got K analyses, 2K minus 1 boundary points, and these funny constraints. That's not nice. So if you weren't a statistician, you'd say we do Lagrangians here. We put in some Lagrangian terms to make this a well-defined problem. Without the constraints, then we have to come back and put some, choose the Lagrangian multipliers in a way that gives us the alpha and the beta that we want. It turns out when you look at this as a statistician, you can say, well, it's a bit like solving a Bayes problem where I put a certain prior on theta and defined cost for sampling and cost for making an incorrect decision, a type 1 error if theta is 0 or a type 2 error if theta is delta. It's exactly the same problem. And the nice thing is we can solve it using dynamic programming. And actually what you need is to write some code that will do the nested integrations that Armitage, McPherson, and Rowe did. And then within that, you do some searches, working backwards from the end, for where the boundary points should go to solve your optimization problem. And actually, that doesn't add much work. The real work in the calculation is going from stage to stage. Finding the boundary is pretty easy. Once you've done that, you have to go back and say, well, somewhere in these priors and costs, I've got a couple of numbers I can play with. Let me search over those till I get a procedure with my alpha and the beta that I want. And then by the usual Lagrangian argument, you can say that must be the optimal design. So that works. I mean, I won't go into any more details for now of computations, but I will comment that what's rather interesting is we've had this frequentist problem, and we've found the optimal solution by solving a Bayes problem that we've been Bayes. And it's not just an efficient numerical technique. It's actually demonstrating that there's things called complete class theorems that say, well, you know, the set of admissible Bayes procedures is the class, sorry, set of admissible frequentist procedures is the class of Bayes procedures. And that holds in the sequential setting just as anywhere else. So we've produced a frequentist and a Bayes method. Now, the Bayes problem we've solved may look a little strange, the way the prior and so on are worked. But we have at least got a Bayes procedure. Now, since then, Bayesians have looked at this. Well, even earlier than that, Bayesians have proposed sequential procedures, and some of them have optimized them. And it's rather strange because you could try very hard to elicit your priors and decide on a decision theoretic way what the cost function should be. You do all of that, and you find you've got a procedure with type 1 error 20% and power 0.98 or something. And you say, well, that's no good. The regulators will insist that the type 1 error is 0.025, and the sponsor says power should be this. So you calibrate it. So you actually work in eliciting priors, and you put something else in. And if you do it properly, you'll get the method that I got, as long as you've got the same objective in how you minimize expected sample size. And if you don't do it that way, you'll get something which isn't quite as good as the frequentist procedure, which is a better solution to your Bayes problem than your Bayes solution. So this, I think, is a convergence. It's saying that Bayes and frequentist should end up with the same sequential designs. And if they argue otherwise, I don't think they're right. That's an aside. But it goes back to Anscombe's contribution of, we should be Bayesian. Well, the big difference, though, is the problem we've solved is this testing problem, not the treatment selection problem. And the real question is which of those is the right formulation. Having done all those calculations, here are some numbers just to show you the sort of things that we learn. So in this table here, I've got the minimum, I've been taking the expected information both at my null hypothesis theta and the alternative delta where I'm trying to get my power. So this is just one possible choice. And everything is a percentage of the fixed sample size. So 100 would be exactly what the fixed sample size procedure gives you. So these numbers are less than 100. So we're doing well. And if you look down one of these columns, I've fixed this inflation factor. So even with a 1% inflation in maximum sample size over the fixed, I can reduce my expected sample size, depending on the number of analyses, 2, 3, 5, 10, quite a bit. If I don't mind going up to plus 5%, which isn't really much of an increase, I can do rather better. And maybe between 5% and 10%, you want to stop, because actually, if things get better, it's not by much, and sometimes they start getting worse eventually they get worse as R increases. So this can guide you to a good choice of maximum sample size. And then if you look down a column, you can decide how many interim analyses it's worth having. And I would say 3, 4, 5 is the right kind of ballpark. The returns start to diminish after that. I'm a bit disappointed to read, I think it's one of those FDA guidances saying 2 analyses is quite good. Well, 3 is better. You've got to balance the costs of getting your monitoring committee together and paying their airfares for an in-person meeting and getting the CRO to do the analyses, or saving 100 patients at £30,000 each in your study. So it depends how those costs work out. But I think a few more analyses is a good thing. But the point is, a table like this allows you to make an informed judgment. Now, these are designs which I don't think anyone ever uses, because you have to run my program and find out what the boundary looks like. Plus, they assume equal increments in information. Nowadays, you'd say we want to use an error spending test. So the role of this table really is a benchmark. If I have an error spending design, I want it to do about as good as this. Otherwise, I should find a better error spending function. Now, in my book with Bruce, we describe a family of error spending tests, which have a very simple form. We spend either type 1 error or type 2 error as a function of the observed information, simply the ratio of information to the maximum raised to a power. And it turns out, rather fortuitously, I suppose, this gives a family of designs which are really good. And as you change this number, it's 2 here, but it could be 1, it could be 3. You go from having more early stopping to less early stopping. You go from things that look a bit like Pocock to things that look like O'Brien and Fleming. But there's a one-to-one relationship between this power rho, we call it, and the inflation factor. So it's a trade-off between maximum sample size and expected sample size. And in this paper with Stuart Barber, we showed that actually whatever function you put in here to optimize, this family will get within 1 or 2% of the best possible results. So why look anywhere else? And there's a graph. So the red line, what are we plotting? Average. This is an integrated expected information this time. Plotted against this maximum sample size R. So the red line at the bottom is the best you can do, these optimal designs. The row family is the kind of purple thing just above that. And what's happening as we move along with R, the value of rho is changing. So we're always within a couple of percent. There is another family, the gamma family of Huang, Shi, Dekani, a little bit more complicated to write down, actually does a little bit better. So you might like to look at that. And then up here is a family that Huang and Sayatis introduced, which looks nice. It's got a nice parametric form. It turns out it doesn't actually do quite so well. The other thing I'd say about error spending tests is that there are some formulae you can use that give you something that's a bit like a Pocock boundary or an O'Brien and Fleming boundary. And they're quite popular. But those are not great tests to mimic in the first place. So I don't like those. I did have a referee's report I got to deal with recently where we used a rho equals 2 design. The referee said, why didn't you do a O'Brien and Fleming error spending function? I'll have to write back, say, because this is better. But, you know, things get entrenched and people are familiar. Okay, so we can optimize. And there's a picture of a typical sort of boundary. So now it's a one-sided test, and it does come to a point. It looks sensible, right? This particular one, it's got a bit of a high inflation factor, plus 13% on the fixed sample size. You might want to push rho up a bit, make it 2.5, push that down a little, but that's your choice. Let me just say that methodology for optimizing designs is very flexible. You can, once you can do that, you can tackle other problems. You can nest the whole thing in some kind of search and say, if I don't have equally spaced analyses, can I do better? Maybe have some a bit earlier or some a bit later. You can even make the group sizes data dependent. If I'm close to a boundary, maybe I want to have another analysis soon. If I'm in the middle, maybe I wait a bit. This is why I mentioned earlier that, you know, there are adaptive group sequential tests and non-adaptive group sequential tests. This would be adaptive. And that was quite a bit of work to do that. And what we found is that actually you don't really gain anything by any of this. Maybe a couple of percent of the fixed sample size. This was an important thing to look at because it relates to methods of sample size re-estimation, which are basically doing this, and they claim to be wonderful. And we can show, well, actually, you're not going to beat a standard group sequential test by much. And since you didn't optimize in the way that we did, you're probably quite a bit worse, actually, for all the work that you've done. Other areas of application, I've just got a few to mention here. It's a good thing for PhD students to do, get into different sorts of problems. So that was my contribution to efficient designs. There's a lot more one could talk about. So if we had time, you know, we could talk about any of these subjects for another hour or two. Inference after group sequential test. The sample space is quite peculiar, so funny things happen. In fact, Peter Armitage wrote about this way back in 1958. And the same ideas are really used then to try and get unbiased estimates, given that you've stopped when you're on a random high or a random low. You want to correct for that. Or a confidence interval after a sequential test. Pipeline data, that was listed in one of these papers here. Lisa Hampson worked on this in her PhD. What I mean by pipeline data is the fact that when you have an interim analysis, well, the data were probably locked 2 months earlier while they got cleaned, so things have happened. There are more observations to report. In a survival, or in a time to event study, I was involved in one where there was an adjudication would take place. The question was this a MACE event in a cardiac study? And there's a number of events waiting to be assessed. So in that particular case, we knew if we stopped at an interim analysis, there would be another couple of hundred events maybe coming in that should then be analyzed later. How do you allow for that with a group sequential test that seems to have stopped and made a decision already? So Lisa worked on that, and it's kind of interesting. The whole field grew up pretty much ignoring that problem. There is interest in doing something about it now, and I think we've got some proposals. What else can you do? Multiple endpoints, multiple treatments, flexible designs. So I will say a little bit about this. How are we doing for time, by the way? What's 10 minutes? Good. Yeah, that's good. I say when I was looking into what I would do my PhD research on, and I thought about combining testing and some sort of estimation, one could take the idea of a repeated significance test and simply make a repeated confidence interval to give you things you could look at an interim point in a study that were adjusted for the repeated looks, but could be treated as confidence intervals. And Bruce and I had an RSS red paper, and Peter Armitage was the proposer of the vote of thanks. And he was very kind. There were some other people who were not so kind. That's a tradition of those meetings. But Peter was excellent. David Cox was also very nice. He just gave us another research problem to work on, which was to do with multiple endpoints. Yeah, but I think we were a little bit ahead of our time, because we were saying you should be a bit more adaptable and flexible, and other people have been working very hard to get people to do anything at all, saying you've got to tie it down and do it properly, otherwise you'll run into trouble. So then adaptive designs came along, and it's pretty clear that this is an idea that fits into that framework. And well, I commented a bit about sample size re-estimation. That's not my favorite area of adaptive design. Although, in the end, Bruce and I went into that and said, well, we don't like what's going on, but if we did have to do it, how would we do it? And we seem to have made some convergence there, saying, well, we can do promising zone methods, but you should get the sample size rule from a different way. One thing that can go on in these designs is there's real scope for Bayesian input. On the one hand, you've got your type 1, your type 2 errors to worry about, and you probably want to tie those down in a way that doesn't depend on leaving it in a prior, well, a type 1 error. It's a different concept. But there are still lots of parts of the design that you can play with, and you can optimize. And when you do that optimization, there are lots of things you don't know, so it seems very sensible to put a prior on them, make a utility, and try and make choices that do that. So I think there is a coming together there, and I would rather do something obvious to tie down my type 1 error rate and then optimize within that than do something completely Bayesian and then say I have to go back and change lots of things to calibrate it to see if I can get alpha and beta back again. And I think the real growth area now is going to be not just multi-arm, multi-stage, but basket, umbrella, all the paraphernalia of these master protocol designs. I just want to say a few things about promoting methods, because it was clear that, what we've heard about Peter's work, he worked with people. He made sure that he was getting the right ingredients and then explaining to people how they might do it and writing a book that obviously had a following. And I think John Whitehead in the UK, certainly, well, broader than that, but basically had a big influence with his work. So this was his book. Bruce and I mean, it's 25 years ago now that we wrote our book. It seemed to pretty much cover what was important. Things had developed properly to maturity in group sequential methods. What we didn't know was adaptive designs were around the corner. And so now there are books on adaptive designs, and we've got a picture of our front cover of our second edition, which you can see has adaptive in the title, and it's nearly written. Right? I know I've been saying that for a long time, but it's almost there. And so we've grown quite a lot in volume by adding a bit to the developments in group sequential methods, but also having whole new sections on adaptive design. And I think this is key. And I would say to the young researchers here, if you want to get your work known, you can write all the papers you like and publish them in the best places, and some other academics will read them. If you really want people to use what you're doing, you need to go another step and help the practitioners write in a way they can learn. And put a nice picture on the front with some sheep jumping over a sequential boundary. Software, obviously, was crucial. John Whitehead's PEST was very popular. Cytel East, I think that was rather more expensive, but very important. And and the work that goes with it, the people doing this, producing the software, were out there promoting it and working with end users. And now there are more things. I mean, this is just a short list. Kevin Anderson wrote his program. Gernot Bassen wrote AdPlan, but it got taken over by eventually Berry Consultants, the latest phase. And he's now gone back and written a free version, well, not quite the same, but free software in RPact, which I think is taking off. And engagement, I say collaboration, consultancy. As academics, we've got to look beyond our desks and the nice maths, talk to people, try and make sure we're working on problems that could be important, and helping in whatever activities to get methods used. And don't forget the learned societies. PSI has a great role in this area, and I was very interested to read in John Lewis writing to say how, so statisticians in the pharmaceutical industry, it's an industry organization. When it was being created, there was a question, well, shouldn't it just be a section of the RSS? They do this sort of thing. And Peter was apparently the one academic who said, I think this is a good idea. And you look and see what they do now, and you realize it was. And there are other societies too. And people have to get involved and help run these things. And as we saw, Peter was president of at least 3 big societies in his time. So to conclude, I've tried to describe Peter's work, but let me just reflect on other talks as well today. He was a scholar, a mentor. And I think what comes through is he was a kind, compassionate person. So he could be involved in, well, heated or enthusiastic debates, but the way he conducted himself was a lesson to us all. Thank you, Peter Armitage.